So Norm, this is it ends at 4. Is that
Yeah, so the seminar ends at 4 Eastern time, and then usually it'll go long a little bit, I think, and that's fine. And then afterwards, people will join the post-seminar discussion. So you just join the other Zoom link that was sent.
all right?
Okay. All right, I think the time is hit, so let's start. Welcome everyone to the VAMOS seminar today. It's my great pleasure to introduce my good friend Ashvin Vishwanath as our speaker for today. Ashvin did his PhD at Princeton working with Duncan Haldane and a postdoc at MIT afterwards as a Pappalardo Fellow. After that, Ashvin joined the Berkeley Physics Department in 2004, and I was super lucky to have him as a next door office neighbor for a couple of years. More recently, in 2016, Ashvin joined the Harvard Physics Department. Ashvin has made seminal contributions to multiple areas in condensed matter and many-body physics, ranging from deconfined quantum criticality to important predictions about quantum materials such as Dirac and Weyl semimetals, high-temperature superconductors, and magnetic skyrmion phases. More recently, Ashvin's group has also made important discoveries in the context of topological insulators, flow K phases of matter, and magic angle bilayer graphene. For these advances, Ashvin has been awarded numerous prizes and honors. I'll just mention a very quick few. A Guggenheim Fellowship in 2014, the Europhysics Prize in 2016, and just recently being elected to the American Academy of Arts and Sciences this year. As we'll hear about today, Ashvin's breadth of interests and expertise is pretty extraordinary, and his group has recently been involved in the prediction of spin-liquid phases in the context of Rydberg tweezer arrays. We look forward to your talk, Ashvin.
Thanks, Norm, and thanks to all the organizers. I think this is the last of your seminars this year, so hopefully I will have something new to say. In fact, one of our papers that I'll talk about is something that is not yet out, and it'll be nice to get people's reactions to that. So I've given a somewhat broad title about creating highly entangled quantum matter, quantum states in synthetic matter. But I'll begin with what is now slightly older work that you may have heard parts of already. So I'll start with an introduction to long-range entangled states, topological order, and tell you why these are of such great interest to people like me. And then I'll switch and talk about our proposal for implementing some of these states in Rydberg cold atom Rydberg lattices. And just recently, this work was published. In fact, I think just came out yesterday. The experimental implementation, and you may have seen some popular descriptions of that. So I'll try to tell you a little bit about that experiment theory collaboration as well. But hopefully I will also have time to get to part 3, which is some new approaches for creating topological orders, including fractons, using these Rydberg atoms. And I think we have now a better understanding of really what it takes to create these very unusual states. All right, so to begin, like many things in condensed matter physics, begins in quantum many-body physics, begins with Phil Anderson. He gave us this slogan of more is different, and I actually went back and looked at his original article, and what he was really talking about was broken symmetry. If you look through, this is really what he has in mind when he's thinking about collective phenomena, what happens when you bring many particles together. But very shortly after, just a year later, he actually came up with the first example of quantum many-body state, which is an example of this more is different, but something that has entirely different character from a broken symmetry phase. And he called it a resonating valence bond insulator. And this is what we now call a quantum spin liquid, a toric code, topological order. We have much better theoretical understanding of it. But the thing that's somewhat surprising is that despite all these years, we don't really have a very good experimental handle on these states. So to set the stage a little bit for you, within this more is different framework, there are many different kinds of ways in which you can distinguish states. There are the symmetry breaking phases that he first talked about. And there are two other pieces to this pie that are very different. One of them is topological order, which is what will be the subject of this talk. And another, which is what goes under the name of topological phases, probably with a qualification, something like symmetry protected topological phases. So these are like the integer quantum Hall effect. And often these two are kind of rolled into one another, topological order and topological phases. But in fact, they couldn't be more different from one another. And they are as different from each other as they are from conventional symmetry breaking phases. Okay, so in fact, in this talk, all three of these will make an appearance. And there's some intimate relations between them that we are still understanding, in fact. But the main focus will be on how to create topological order. Okay, and topological order, in a word, what it means is that you have excitations, which are anyons. They have properties unlike the regular matter that we are used to, unusual statistics on braiding, and many other unusual properties. Okay, so there are examples of topological order. They're few, far between, and really all of them appear in some sense or the other in the fractional quantum Hall states. Okay, so fractional quantum Hall, you have a two-dimensional electron gas, extremely high magnetic fields. You see this is like the x-axis here is Tesla. We're interested in states like this one over here, the Laughlin one-third state, the one-third fraction. You go to very low temperatures. You can see the temperature over here, it's in millikelvin. And then you see these exotic effects. Okay, and you see this measurement of this one-third Hall conductance tells you the electron has been fractionalized, and you have non-trivial anyons, all of these unusual properties. Okay, so this is a successful example of a topologically ordered state. And you see although it is at finite temperature, you could argue that this is a state that's only realized at zero temperature. This is something that, of course, you cannot quite reach. There's an energy scale in your system, which is the energy gap. It's of order 8 Kelvin in this particular system, and you're well below that temperature. Okay, so if you want a benchmark of what it means to realize topological order, this is kind of the gold standard. And any other example, we'll be trying to achieve the kind of success that we've had with the fractional quantum Hall effect. Okay, it's there from the Hall conductance, and the relevant energy scales are well above the effective temperature. Okay, so that's an established form of topological order, but there are many, many kinds. And the one that Anderson first proposed is a variant of that. It's somewhat different from the fractional quantum Hall effect. And he called it a resonating valence bond liquid, where pairs of spins, so the setting is much more a solid state physics setting of a material with spins. They form a singlet, they form a pair of spin and a half forms a singlet. And then these singlets quantum, they resonate, they move around under quantum fluctuations. And this state, Anderson sort of proposed is going to be something exotic. Although all the properties were not known, he called it a resonating valence bond, and it should have exotic excitations. Okay, but unfortunately, this particular model that he came up with, and many others that people proposed, they don't quite realize the state. Okay, they tend to order, and that's going to be one of the main things we're going to try to fight. The tendency of things like spins to simply form an ordered state rather than this unusual resonating valence bond state. Okay, now there's been many attempts in solid state physics to find something that did not order. One of the most successful experimental programs in this direction has been trying to isolate a very clean version of this material, Herbert-Smithite, which shows many anomalous properties. It's a spin-and-a-half magnet on the Kagame lattice. There's been a lot of progress, but I would say still, we do not have a very clear-cut example of a quantum spin liquid. Okay, something which not only fails to order, but also shows some positive signatures of quantum spin liquid behavior. Okay, so that's kind of the stage. And you can ask why is it so hard? I kind of alluded to one of the issues. So if you had ordered states, of which we have many, we know how to measure and tell that there's an ordered state. X-ray scattering will tell you there's a crystal. You can use that measurement, that way of measuring, to classify all of these states. And there are actually many applications just having this order parameter, which we sort of take for granted. Okay, starting from the rigidity of solids to magnetic memories and so on. What about topological order? One of the main problems in identifying topological phases is that they're pretty subtle to identify, to really get a handle on. The quantum Hall effect is an exception. They're just measuring the Hall conductance, very easy to measure, relatively speaking, already tells you unambiguously that you have a topologically ordered phase. But if you have one of Anderson's RVB states, the positive signatures are less obvious. Another thing we mentioned is it's hard to beat order. So you really need platforms where you have a lot of tunability. If you find some regime of parameters are not good, you're getting an ordered state, you should be able to wander around, should be able to characterize it, and things like that. And if you succeed, there are applications much more subtle, just from the nature of these states, ranging from quantum memories that are protected to maybe new ways to get superconductors and so on. So it's certainly a worthwhile goal. And one thing we can kind of take heart from some cause for optimism is that if you look at solids, the ordered states, there are many different ways in which they can crystallize. 230 space groups, but in fact, there's a mineral in each and every one of those space groups. So, if you wanted some encouragement that nature is going to do anything that's not forbidden, maybe we can take it from that. Okay, so we said that at least at the atomic scale, from electrons, this has been challenging. So we're talking about systems that are at the angstrom scale. Ideally, we'd like to get a spin liquid in that regime. But recently, there have been these synthetic systems that at least I'm extremely excited about and optimistic about. One of them is Moiré superlattices, and in fact, there are indications of some of these kind of exotic states beyond the fractional quantum Hall effect over there. I often give a talk which combines these two. But today, because it's a cold atoms seminar, let me focus on the second, and optical tweezers, and quantum gas microscopes that give you artificially generated lattices, and with a high degree of tunability, and with interactions that we don't naturally associate with spins and solids. Okay, so it's a new playground. It's highly tunable. It's still not, it's still not everything. It's still not every possible knob under your control, but you have a lot more control than you normally do. Okay, so the thing that I will focus on are these Rydberg atom arrays. So this is, of course, you've heard talks about this in this very seminar series. So you can load lattices very accurately with atoms, with say rubidium atoms, and you form a qubit. Either you're in the ground state or a highly excited state of these atoms. So although these atoms are relatively far apart, it's an optical lattice, microns apart, or order of micron apart, they still interact. And that's because you excite them into these very highly excited Rydberg states, and you get a qubit. And these qubits can make up a quantum many-body system, somewhat like a spin system, but with unusual interactions. Okay, so how do they interact? So really, the heart of this is that you drive all of this with a laser. Particles are going between the ground state and the excited state. If this is the qubit, sigma z, then this is a term that is sigma x, and the Rabi frequency is the coefficient. The detuning from resonance is the coefficient of sigma c. So you have these two parameters that you can tune at will. Of course, if this was the Hamiltonian, it would be rather unremarkable. What actually makes this interesting is the feature of the interactions between the Rydberg states. And you can, to a first approximation, you can model this interaction as what's called a PXP interaction. Okay, so the resonance between the ground and excited state is disturbed if there are neighboring atoms that are also in the Rydberg state. Okay, so you've got to make sure the neighbors are not excited before you can make an excitation of an atom. Okay, that's the projection operator. And of course, this requires a radius. You've got to specify how, what is the radius of influence. So there is a Rydberg radius that we'll keep referring to. That's the circle over here. And the projection operator says that no atoms in this region should be excited if you want the central one to oscillate back and forth. Okay, we'll later use a more realistic form of the interaction, but this is a good starting point. Okay, so here's the idea. Maybe we can use these Rydberg systems to make models of quantum spin liquids. And in some ways, they are ideal because you can think of these valence bonds as being some dimers that sit on the bonds of the lattice. And the dimers don't like to have any neighbors nearby. Okay, so if I take the spin and form a singlet, the neighboring bonds do not have a singlet. It's reminiscent of this kind of blockade physics. Okay, and if you're able to do that, that's the first step. You've then got to get into this liquid state. Can you do all of this in a Rydberg system? Okay, so in other words, the way we talk about it is, is it Rydbergable? So you have a lot of tunability, but you can't do everything. So let's imagine you have the space of Rydbergable Hamiltonians. You have these systems that have a dimer description, this in terms of these degrees of freedom that touch just one site. Some fraction of these are actually quantum spin liquids. Is there a non-trivial intersection between these two circles? First step is to get this dimer description. Second step is to make sure that the limited dynamics that you're given, that you're provided, this omega term, is sufficient to melt those, that dynamics can actually give you this quantum disordered state. Okay, so each of these turns out to be non-trivial, but what I'll try to argue is that this intersection is small but non-vanishing. There is something there living in that intersection. Okay, to give you some idea of the challenges, the first thing you need to select is the lattice where you're going to put your atoms. The second is the Rydberg radius. Okay, so for example, if you try to make a dimer model on the square lattice, you would pick atoms at the centers of these bonds and put dimers. But you'll see that if you try to pick a Rydberg radius that does this for you, you don't actually succeed in getting a dimer model. You get something else because the sites, the atoms on neighboring sites are actually they would end up being allowed at this particular Rydberg radius. You simply can't get the dimer Hilbert space, and in some sense, even the first step you fail. You cannot Rydberg realize this the square lattice dimer model. Okay, so what does work then? So it turns out that fortunately you can realize this on the Kagame lattice. Okay, so if you wanted dimers on the Kagame lattice, the strategy is to put the atoms on the midpoints of the bonds, and now you check, you do some geometry. This is kind of the moment of truth where you see if this thing can be made into a Rydberg blockade kind of constraint. And in fact, just the geometry of this Kagame lattice turns out that with this particular Rydberg radius, 2 times the nearest neighbor distance, you indeed find that the allowed configurations, if you put them at full filling, put in as many of these excited atoms as possible, they precisely map to the dimer configurations of the Kagame lattice. So this is Anderson's dream of getting spin singlets on the Kagame lattice. Instead of spins on the sides of the Kagame, you've got to take this dual viewpoint, go to the midpoint of the bond, put a Rydberg atom there that's going to represent this valence bond. And then you find that with this particular Rydberg radius, you would get the right dimer Hilbert space. So step one, you have managed to satisfy. There are not a whole lot of other examples. So some of them are listed here by others. But this has a second feature that's very favorable. That's the second thing that we need to check. But before I do that, this lattice over here is not actually the Kagame. So sometimes people say this is spin liquid in the Kagame, but actually the atoms form a different lattice, and it took us a while to find the name. It's called a Ruby lattice. Okay, so it's some projection of the Ruby structure into 2D. It looks something like this. You really need your atoms on the Ruby lattice Hilbert space, take the Rydberg radius, Rydberg blockade 2 times the nearest neighbor. And the claim is the Hilbert space is that of dimer model on a Kagame lattice. Okay, but that just gets you halfway. The next step you need to do is to show that this thing actually melts and gives you a quantum spin liquid. Okay, and To do that, there's no way to avoid doing numerical calculations. So we put this system on a cylinder, and we do DMRG calculations. And in fact, initially, I should confess, I was not very optimistic because this model seemed so far away from some exact solution that was present that it didn't look. What are the chances, right, that this will actually realize for you a quantum spin liquid? Okay, so in fact, if you start with small delta, you just start with you kind of scan this phase diagram as a function of delta over omega. In the extremes, if you have delta very large, you completely populate this dimer covering, and you don't have much room not much wiggle room. It turns out you get some kind of crystalline phase. That's kind of the bane of these kind of models. They end up ordering in some way. If you go to very small delta, very small detuning, you get a lot of monomers. You get a lot of defects in this dimer lattice, and they kind of condense. They give you some trivial state. Okay, so that's not good either. But what Rubin found is that if you go in between, you find that for no obvious reason, there's a transition, and there's another state which looks pretty disordered. Okay, so if you look at the density of excited states, they look like a liquid. It's pretty uniform. It also looks like that in this trivial phase, but for some reason, there's a very obvious transition when you go from one to the other. Okay, so this is kind of smells like a spin liquid. It looks disordered. It looks like a liquid, but it has some hidden topological properties that are hard to see. And the question is how you're going to expose that. And this is really what Rubin did in a series of very beautiful numerical studies on this Ruby lattice. Okay, so in fact, I like to call it the Rubin lattice after all the stuff that he's done for it. All right, so so what should we expect, or how should we think about this state, and that will eventually give us the signatures? Well, we're thinking of this as a condensate of loops. Okay, so why is that? Of course, we have this dimer covering. You can pick a reference covering and look at anything relative to the reference, okay, by superposing them. When you do that, simply because of this constraint, you get closed loops of dimers. Okay, sometimes the dimers can cancel, but everything shows up as a closed loop or no dimer at all. So really, this quantum spin liquid we're talking about is a condensate of these loops. Okay, and roughly speaking, you can think of these loops as electric fields. That's a more useful description of this rather than in terms of the individual Rydberg excitations. And these electric fields, because of a Gauss law, they form closed loops. Okay, and this is really a kind of quantum electrodynamics, except that the electric field is a mod 2 valued quantity. So it's sometimes called Ising electrodynamics, Ising gauge theories, Z2 gauge theories, etc. Okay, so we all know how to detect ordered state. We knew, at least we were taught how to detect BECs, right? Particle condensates. You do this beautiful experiment, time of flight, you go and measure the occupation of particles in the zero momentum state. That was, 2 decades back. Now what you're being challenged to do is to do something analogous for a condensate of loops. Okay, so where the objects that are condensing are not particles, but these extended objects, but they're kind of fluctuating around and they form the loop condensate. And unfortunately, there is no simple analog of this, pre-expansion kind of experiment to show these nice pictures. You'll have to work harder to expose this loop condensate. Okay, but it's possible, and that's really the task that is before you if you want to establish a quantum spin liquid. Okay, so some intuition for this can be got from the Toric code. Actually, I see there's some. Maybe I'll pause for a second over here if there are any questions. I see there's something in the Q&A, but
yeah, perfect. Maybe there's a number of questions, Ashvin. So this is a good stopping point, maybe for just a second. Then I can ask a couple of them. The first question is more of a clarification question. There's a question that asks, so initially we started thinking about spins sitting on vertices and singlets between spins on vertices, but then it looks like we went to spins on bonds. When is it right to think about singlets on bonds as the dimer and spins on bonds as the dimer? Are they both equally good?
Yeah, that's a great question. So initially, the initial proposal was for singlets between the sites, and the singlets lived on the bonds. But actually, Anderson had another paper a couple of years later where he took the other point of view that you have a spin which preferentially points up or down. So it's like an Ising spin. And then you can represent that spin if you draw a dual lattice. And if you have the right interactions, you can represent that spin itself as being the presence or absence of dimer. So one of the big advantages you get is that the spin singlets that formed the dimer before, they are composite objects. And keeping track of them is hard. It's hard to have an intuition what exactly they're going to do. But when you switch your viewpoint and think of the dimer itself as a quantum variable, but just, it's either there or not, many of these pictures carry over. And in fact, in some sense, the essence is in the pictures, in these cartoons that we draw. And what exactly constitutes the dimer is less important.
Got it. Aruku Seno has a question about the relationship between topological order and spin liquids in general. Should one think that some spin liquids have topological order, or is topological order a defining feature of all spin liquids?
Yeah, that's a good question. So there is some confusion about this word spin liquid. I think the most reasonable way to define a quantum spin liquid is something that not just is disordered, but also has some emergent features that you cannot capture within a classical kind of picture. Now, that still leaves room for a lot of different kinds of spin liquids. And I think it's fair to say we don't know all the different ways in which that can happen. We know two different distinct types. One is gapless spin liquid. There's no energy gap. And then there are the gap spin liquids. So the ones I'm talking about and the ones that when we say they have topological order, we're referring to the gapped spin liquid. So it's a subset of spin liquids, but it's the subset where, if you were to begin, that's where you have the most chance of actually understanding things. And the gapless ones are even more complex.
Got it. Adam Kaufman has a question related towards the end of what you were just talking about. Normally, I think about condensates as being bosonic. Is there something bosonic about the loop condensates that you're talking about?
Yeah, that's a good question. Yeah, in a sense, they are bosonic, but because they are not particles, this is at best an analogy. So loops are really different. I mean, they're extended in space, so you cannot refer to them by position. And then the question becomes, when you try to exchange them, what happens? All of these things are need to be reworked. But just like there are different kinds of condensates, 230 different space groups, different ways of breaking spatial symmetry to get crystals. You can use some consistency conditions for loop condensates and try to classify them. And people have done that, and it's been pretty successful with some additional conditions. You need to have some rules about how loops can enter and exit the condensate, how they interact with one another and with themselves. And these very simple kind of considerations strongly constrain the kind of loop condensates you have. So we have a different language for them rather than bosons or fermions. There's a different language, which is really the kind of topological order that you get. And one of the simplest kinds is the Z2 topological order.
All right, two last very quick questions. Francisco Machado asks, it seems like there's a pretty simple geometric design principle for how to get these dimer phases, analogy to the Rydberg. Are there other lattices, or is the Kagame bond spin version the only one that is known?
That's a good question. So actually, there's one more piece of information that I didn't highlight, which is that you actually want a dimer model on a non-bipartite lattice. So if you refer back to the vertices that are connecting, that are at the vertices of this dimer model, you should not be able to break them up into A and B sublattices. And the reason is it's kind of a deep result that was established early in the days of quantum spin liquids by Nick Reed and Subir Sachdev, various people, that when you have magnets or when you have dimers on this kind of bipartite lattice, the tendency to order is much stronger. And it kind of it completely beats this quantum spin liquid phase. So your only hope, that window is again narrowing now. So you've got to be on a non-bipartite lattice. With that extra provision, I think we have maybe one or two other examples in 2D, but they're not a lot. But if you know how to find more, that'll be great. In 3D, it's a different, it's a different game. And 3D, you're allowed to do bipartite as well. You can have quantum spin liquids on bipartite lattices,
Awesome.
but restricted to 2D.
Good. One last question, again from Aruku. He asks, normally I think about DMRG being for one-dimensional systems. I don't understand exactly what you mean by projecting a two-dimensional system onto a cylinder.
Yeah, you just take periodic boundary conditions in one direction. It's not you're restricted in that dimension. You can do maybe 8 or 10 or 12 sites around that direction, but you can do an infinitely long cylinder. And you've got to do finite size scaling and try to approach the thermodynamic limit. One thing that's nice about these gap phases is there is an internal quantity that you can calculate called the correlation length that tells you how good your approximation is. And if the correlation length is much smaller than the circumference of the cylinder, you're in good shape. Otherwise, you may be being affected by finite size effects. But we have very short correlation lengths. So, that spin liquid I showed, it's got about a lattice spacing correlation length. So you're pretty confident that you're in the spin liquid.
Great. There's some other questions, Ashvin, but I think we'll let you continue for now and maybe ask them towards the end.
All right. Okay. So I was telling you, getting some intuition from the simplest model that defines the spin liquid phase. The toric code has this particular Hamiltonian. It's not super realistic because there are 4-body interactions. When you do this, when you take the 4 bodies in this particular form, you can solve it exactly. You find a phase diagram that looks like this when you perturb it with fields. So you can solve this point exactly, perturb it with fields. And the fields are large. You're just in a simple confined state, product state of the spins. But when the fields are small, it's really these 4-body interactions that take over. And you find there's a phase transition into some new phase. And that's really the spin liquid or the topologically ordered phase. Okay, so this is the simplest model we can think of, which has the state. And the question is, how do you tell these two different states apart? Of course, one is you start in one and you go to the other, and you see there's always a phase transition. But you want something which, if I give you a point in that phase, you should be able to diagnose and say it's in the topologically ordered phase. Okay, so people have come up with some ideas for how to do this. If you take this particular path, the very special path that hugs this boundary, so you only use one of these fields. There's something called a Wilson loop. It's an operator that looks like this, product of spin operators around this loop. You make that loop very large, and you calculate its expectation value, how it scales as you make the loop larger. And what you find is that its behavior changes. Okay, when you're in this topologically ordered phase, the quantity is rather big. It only decays as the perimeter of this loop. But once you exit and go into this trivial phase, it turns out to have a dependence on the entire area of this loop. Okay, so it's somewhat like an order parameter once you make allowance for this perimeter versus area law. Now, unfortunately, when you move off that particular line, you don't have that convenient access anymore. You cannot look at this Wilson loop. It fails to distinguish the difference between these phases. Both these sides end up having perimeter law. Okay, so you have to invoke something else, and there are ideas. For example, if you put the system on a torus, you have ground state degeneracy. That's called topological order. You can look at the topological entanglement entropy, look at anion excitations, modular matrices, whatnot. But most of these are really numerical things that are really suited for numerics. So in fact, in our numerics, the way we tell that this is a quantum spin liquid phase is we put this on a cylinder and we calculate the entanglement entropy. You divide the cylinder into two, calculate the amount of entanglement between the two parts, and see how it scales. Does it scale as the circumference? Usually there's a part that scales as circumference, but then there's a subleading piece. And all the information about the non-trivial topological order is in the subleading piece, which you can try to extract. And if you're in the trivial phase, you find the subleading piece is just 0. But if you're in this topological phase, it nicely extrapolates and you get a quantity which is minus of log 2. That's the units over here. That's what is expected for this topological entanglement entropy. Okay, so you can do this in numerics, and this is how you tell. But we are ultimately interested in an experimental manifestation of this. So we'd like to see topological a way to do this, which is accessible, and that's really given by these topological string operators. Okay, and that turns out to be an advantage of these synthetic systems. Not only are they tunable, you can have access to observables that you don't normally have access to. I'll describe this in a little more detail. Okay, so I already mentioned this topological entanglement entropy. So one thing I should mention, there's previously I would give this talk and say, there's no way you can get this in an experiment, but turns out there is an experiment that has gone and measured the topological entanglement entropy by the Google group, of course, on very small systems, but they have a very good Tory code state. And I think, again, that paper just came out yesterday. So this is a possibility, but it's really challenging, okay? So here I'll describe a different way of telling apart these two phases called the Friedenhagen-Marcoux order parameter, FM order parameter. And the advantage is it's much more physical, it's more accessible. Okay, so to give you some intuition why this, how we're going to build this order parameter, let's go back and see how you get an order parameter for a Bose-Einstein condensate. Okay, so what you do there is you take this creation operator for the bosons, you take this correlation function, and then you see there is a long-range order when you separate the two. And the reason this is non-trivial is if I took a single one of those operators, just the B operator, for example, that is just zero when you take the expectation value. Okay, that's why it's really the pair is non-trivial. There's a symmetry that prevents the B from having an expectation value. But when you see the pair having one, that means it's a long-range order symmetry broken state. There's an analog for loops. Okay, and the analog is you take a loop that is this closed loop, take its expectation value, and when we say it is long-range ordered, we're really talking about this perimeter law. It has a perimeter. You discover it has a perimeter law. But for this to be a non-trivial statement, you need that sort of the operator that is half of it that you divide into two. In other words, the open string operator, you need that to be zero. Okay, so this is really this Friedenhagen-Marcoux order parameter. If I have an open string, it behaves very differently compared to a closed string of the same length. Okay, so a slight subtlety over here is that all of these things decay with their perimeter. So you need to take that into account. But once you normalize for that, take a closed loop of a certain parameter, take an open loop of the same parameter, you'll find that the open loop will decay much more rapidly if you're in this topological phase. But the two will decay roughly the same if you're in the trivial phase. Okay, that's kind of the ratio is really what is important in kind of figuring this out. Okay, so this is written in a bit more concrete form for our particular state. So we have these dimers that live on the bonds of this system of these triangles, and when my loop intersects the sides, I get a minus sign whenever there's a dimer. That's one of the operators that I'm going to define. I'm going to define the expectation value of that compared to square root of the closed loop. And the way this is going to happen in an experiment, imagine that you take a snapshot of these Rydbergs. From every snapshot, you can calculate this quantity, and then you can average over the different snapshots. Okay, so that's one loop. Now, it turns out that in the story code, there are two kinds of loops that you've got to look at. There are two dual loops corresponding to the electric and magnetic fields. Okay, this is, for example, the electric field loop, but there's one corresponding to the magnetic fields. And this turns out to flip these dimers. So it induces quantum dynamics in the space of dimers. And it's completely crucial to measure this operator as well. Okay, this is what tells you that this spin liquid is a quantum spin liquid as opposed to a classical spin liquid. It's not just a bunch of dimers that are thermally disordered, and you're seeing all the different configurations. The different configurations are actually in quantum superposition with one another. And the way to do that is to go and measure a loop that takes a particular dimer configuration and switches it, and see if you have the coherence in that wave function. Okay, so you need to be able to measure both of these. And again, if you do this in numerics, it works beautifully. The loops, for example, in the spin liquid phase, the loop is much bigger in magnitude than the open string. Okay, and you can use the loop combined with the open string to distinguish these three phases. And you have this feature that the open string is small in the spin liquid phase, despite the fact that the loop is big. Okay, so so you can really use this, and in non-numerics, it's a perfectly good way of telling which phase you're in. Question, of course, is how do you do this in an experiment? So the idea is, okay, we have a particular proposal for realizing the quantum spin liquid in an experiment. You set your parameters, you do that, you get it. How do you know you're there? Well, from the snapshots, you can measure one of these loops. You can go and measure, I think what I've called P loop. But how do you measure the dual one? How do you measure the one which is referring to quantum fluctuations? They don't show up in a photograph, right? Okay, so so this is going towards an experimental realization. We want to make sure that realistic interactions, we still have the phase, and how do we measure? Okay, so I won't go into the details of this realistic interaction part. If there are questions, I can talk about it. But this was really took most of the time in this project to really figure out that the realistic model actually has a spin liquid phase. And it's somewhat subtle. The actual geometry of the lattice appears. So you can squish this Ruby lattice in a there's a one parameter family of lattices. And for certain ranges of the parameter, you see a spin liquid phase. And it also depends on how many of these long range interactions you keep. Sometimes you have the spin liquid phase, and then you keep adding more interactions, and it goes away. So you've got to do these really detailed numerics. I think ultimately Rubin ended up keeping 44. Each side is coupled to 44 other sites. So you take all the interactions from the nearest neighbor all the way up to the second, third, and so on up to the 16th neighbor. You need to do all of this in order to really be sure that certain regime of this of the spin liquid is still there in the realistic model. Okay, but these are details ultimately figuring out this phase diagram. But let me talk a little bit about measuring these off-diagonal string operators. So looking forward a little bit, this is the kind of photograph that you get in the experimental. In the experiments, you have a lattice. You have Rydberg atoms at the midpoints of these edges. That's the Ruby lattice. And when it's excited, you draw it in orange as a dimer. Others are in the ground state. And you see it's kind of like a dimer covering. You get many of these snapshots. You can measure correlations, anything diagonal in the spaces. Even if it's non-local, you can measure it. Okay, so one of these loops you can get for free. The question is, how do you get the other one? Okay, so here it turns out there is a very clever trick that we're fortunate, actually, Ruben found this trick that you can actually reduce the other operator, the off-diagonal string operator. You can reduce it to a measurement of the diagonal string if you do a certain time evolution protocol. And it's kind of like a quench. You take your system, you change the Hamiltonian, let it time evolve for a little bit, and then you measure in the original basis. And what it involves is taking the Rydberg radius and shrinking it so that you only interact with these other sites on the same triangle. Okay, so imagine doing that. You shrink your Rydberg radius to that scale. Then you've got to time evolve for a very precise amount of time, 4 pi over 3 root 3 for some reason. And then you go and measure in the diagonal basis. And it turns out this protocol, if you do it for just the right amount of time, you will get, this correlation function tells you that you're picking up some loop correlators at this precise time. Okay, so that in that way you can get the off-diagonal correlators, and that really tells you have some coherent quantum spin liquid. Okay, so that had all the ingredients. At that point, we felt confident we can, go to a respectable, really get some experimental, attention to this. And a few months later, this amazing group of experimentalists, they could make all of this a reality. I think it just took 4 or 5 months before we had this theory and experimental collaboration. But I think what this really shows is that the numerics play a very key part in order to make sure that what you're getting is it's not just some theory that's divorced from the microscopic models, and it's not pure experiment. It's kind of what happens a lot in the solid state search for spin liquids. You really need this tight coupling so you know what you're doing. Okay, so I think Julia already gave a very nice talk on these experiments, so I won't kind of belabor it over here. But essentially, this this fairly large array of atoms. It's still, of course, as a theorist, we'd like it to be even bigger because there are edge effects. But you can already start saying, seeing some nice physics. You have a measurement of these loop operators. So the idea is you start, deep over here where you have none of the atoms are excited, and then you raise the detuning. So you kind of start populating the system with Rydbergs, and you do that in as adiabatic a fashion as you can. And the hope is that when you go through this transition into the quantum spin liquid phase, by unitary time evolution, your state will evolve. If you're really doing it adiabatically, you will pick out the ground state, and you will see the quantum spin liquid state. And of course, this is all done at a finite rate because you're limited not just in the size, but also in the time that you can do the experiment. So you do the best that you can, and you measure this at different points along the way, the size of these loops. The fact that this loop operator grows means that you're getting into this Dimer-Hilbert space. Okay, so that's the first encouraging sign. You can also measure the dual loop autoparameter. It tells you that there are quantum fluctuations. These loops are quantum superposition, and then you can try and find the this ratio, the Friedhagen-Markov autoparameter, where it is 0 for both of these loops is really the onset of the spin liquid. Okay, and that's shown by this shaded area over here. So this is in the experimental paper. Actually, the plot I like is actually in the supplementary. This actually makes it easier to tell what is going on. Maybe I'll just quickly tell you about this. So this is numerics. The clean looking one is numerics, and this one is the experiment. This numerics is not a ground state numerics. It's really doing this adiabatic sweep, okay, with the parameters of the experiment. And what you see is these two lines over here are for the open and closed loops of the same length. So when you're in the trivial phase, you can't really tell them apart. There's nothing topological there, so a loop is a loop. It's just the length of the loop that matters. You don't care if it is open or closed. Okay, so but once you get into this spin liquid phase, you see that there's a divergence. The closed loops are much bigger than the open ones. Okay, and roughly that is what is happening in the experiment, right? And even the onset, the place is roughly okay. Not as big, but given the uncertainties, this is with periodic boundary conditions, this is open, et cetera, et cetera. So you can also do it for the dual loops. They also have this feature. They look the same. They hug each other until they get somewhere over here, and then you begin to see a divergence, and then it becomes smaller. This one becomes small, and this is still non-zero. That's roughly over here. Of course, the scales are somewhat different. That's something we don't quite understand. But it gives a reasonable account of what is going on over here. And when these two are both 0, you would say that wave function has properties of the quantum spin liquid. Okay, so that's kind of the status right now. To summarize this part, this is really a powerful, this platform is really powerful, I think, to generate these non-trivial quantum states, and it raises many interesting questions. What about non-equilibrium dynamics? It's really a sweep. And the first part I was telling you about ground states. That is like doing the sweep with an infinitely slow rate, or cooling the system. If you did one of these two, you would get the ground state. But you do this in some finite time. So what does that mean for the final state that you get? And then can you actually use this? Can you make protected qubits and so on? These are kind of the questions, I guess, for future work. Okay, so maybe I'll pause here for a few questions, and then I'll go to the last part of the talk, which is really the new stuff.
Awesome. So there's quite a number of questions. I don't know that we'll get through them all, but let me try to ask a couple of them. Adam Kaufman asks, given the sensitivity to the long-range interaction cutoff, how robust is the spin liquid phase, and what is the size of the corresponding gap in, say, units of 1/J?
Yeah, that's a very good question. So, the gap is something that we should be able to tell because, that's a property about the ground state, excited state, and so on. So unfortunately, DMRG is not very good at giving you gaps. So we don't have a very good estimate of the gap. I mean, you can get something rough, but we don't really trust it. So that is really something for the future work. But the question of what you actually prepare, it may not be very closely connected. It is related to the gap to some extent. But that is also a separate question. This non-equilibrium dynamics, it prepares something for you. In fact, what it prepares seems to be a better example of a quantum spin liquid than the actual ground state with the same parameters. So if you took the parameters in the experiment and you ran DMRG and you go to very long interactions, you actually find that it orders. It's very close to a quantum spin liquid. So if you were to terminate at the 6th neighbor, you would find a quantum spin liquid. If you terminate at the 9th neighbor, you find that it orders. So there's like a phase boundary that I showed that was kind of anticipating this question. Yeah. So like I said, there are different geometries. Geometry becomes important once you go beyond the blockade regime. So in this particular geometry, which is the Kagome aspect ratio of the sites, depending on what is the truncation radius of your model, you get this kind of canonical phase diagram, trivial spin liquid solid. But that pinches off once you have many more radii, many more interactions kept. Okay, so if you were here, you would actually see that if you went to the ground state, you would see that it's there's direct transition in trivial and this Gillingspan solid. But you're doing this at some finite rate, and actually, when we do this in numerics, we can simulate these models in numerics. There's no big difference in the dynamics from keeping this number of couplings or that one. They look the same. That kind of fine detail is not seen in a dynamics that is as quick or at this rate. So it's a slightly different question that is being asked when you're actually preparing a statement doing the dynamics. It's related, presumably, if you were nowhere near a quantum spin liquid state, you wouldn't get such a final state. But the precise relation, I think we have not really nailed down. In the sense that, if you just give me a model without doing any calculation, I can tell you how good this thing is going to be when you do the sweep. So that is an interesting intersection of non-equilibrium dynamics and topological phases.
Good. Maybe two other super quick questions. Aruku asks, in the experiment, the boundary seems to make up a non-trivial amount of the system. Are boundary effects important? And do they lead to an effectively smaller region of spin liquid that only exists in the bulk?
Yeah, I think that is true. I don't know how to quantify that, but our numerics are done with periodic boundary conditions, infinite cylinder. That's really great, right? There are no boundaries. But especially with these longer range interactions, boundaries are going to be important. So you are kind of wasting this whole region around. It looks like a very big system, but it may actually be the homogeneity issues. May be important to take into account. And instead of just going for bigger and bigger systems, you may actually want to treat the boundaries in a way that makes the termination more gentle. Right?
Got it. There's a couple of questions on this, so I'm going to try to combine them. For the topological entanglement entropy offset, are there any observables or sets of observables that are sufficiently local that they can kind of be measured? And in particular, would it be possible to measure such things in the Rydberg system?
Yeah, so by definition, this topological entanglement entropy has no local counterpart. You're really trying to isolate the part of the entanglement entropy. So first of all, entanglement itself is not a regular observable. And you're trying to isolate the part of it that is not local, the thing that does not scale with size. And that is precisely the topological aspect of this. So somehow by definition, anything local, it's not is not viable as a diagnostic.
Okay. Great. Let's let you get on to part 3. Let me just mention, Ashvin, there's probably maybe 5-10 minutes left. So just keep that in mind.
Yeah. So maybe I'll just give you a little bit of a teaser before maybe I'll stop and take some questions. Let me see where to stop. Oops. Just give me a second. Okay, so so one of the key things that we left off over here was about preparing. Oops.
Ashvin?
Yeah.
I'm not sure if it's just me, but I think that your screen sharing might have stopped.
Same for me.
Yeah. How's this?
Yeah, now it looks good.
All right. So there's a question about how you go from the trivial to the spin liquid, and we're talking about unitary dynamics. And in order to get this highly non-trivial long-range entangled state, which is the topologically ordered phase, you have to go slowly. Okay? And it's really because there's a transition. You have a continuous phase transition, so the gap will come crashing down and then reopen. The gap is roughly the inverse of the system size. So the adiabatic time scales as the system size. Okay, so that's a very generic feature of trying to prepare these long-range entangled states. If you think about it as using a circuit, a quantum circuit, the depth of that quantum circuit is going to grow with the size of your system. That's kind of the time in the Hamiltonian language. Okay, so the question is there a way to prepare the spin liquid or other long-range entangled states? Can you do it fast? Okay, can you do it in a time that is not proportional to the system size? That's impossible if you're doing unitary dynamics. Okay, but we know there are actually two different ways in which we can time evolve a quantum system. One is through the unitary Hamiltonian Schrodinger dynamics. The other is by doing measurement. Okay, that's the part that we, at least in solid state physics, we never actually do. We always do the first one. But in fact, using the second way of doing things, you can prepare long-range entangled states very quickly, and you can do it efficiently. And that is the subject of this paper, again, with Ruben and with Nat, who's a student at Harvard, and Ryan, who's a postdoc at Harvard, MIT, and moving to KITP. So we have two papers. One of them is to appear, and the other one is about getting this long-range entangled states from measuring these symmetry-protected topological phases. So that's kind of the the idea. So just to bring you up to speed, so this idea is not completely new in the sense that there are examples known of precisely this this effect where you can take a system, let's say in one dimension. So here the target state is going to be the GHZ state. So this is a long-range entangled state because you have all of these spins up plus all of the spins down. You want to start from a product state. You can't get there unless you do unitary evolution for a time that's proportional to the system size. But these people showed that if you start with something called a cluster state in 1D and measure half the atoms or half the qubits, the red qubits, let's say, then you will end up on the unmeasured part will end up being a Schrodinger cat state. Now it's almost a GHZ because some of the spins are random, but from your measurement outcome, you can figure out how to go and fix that and get a GHZ state. This whole thing you can do in time that is independent of the system size. I mean, maybe there's some issue with classical communication, so maybe you're restricted by the speed of light or something like that, but literally you apply one single gate, the control Z gate, to go from a product state to a cluster state, go and measure, and you have a Schrodinger cat state, and then you can go and flip it all and get the GHZ. There's something similar that you can do actually to get the toric code as well. Somewhat surprisingly, you apply control Z gates to these, this is some pairs of qubits. You go and measure, if you go and measure the blue sites in this language, you'll end up getting the GHZ state. If you go and measure the red sites, you'll get the toric code. Okay, so these are kind of known, and the question is, why haven't people tried to do this? Well, one of the reasons is, we didn't really have the technology, I would say, but now there are a lot of exciting new developments in Rydberg systems, for example, maybe in other platforms as well that I'm not aware of, that really, I think, make this very timely to look at these ideas and to try to extend them. So, for example, we now have these dual species Rydberg systems. We have them, in maybe in 3D as well. We have arrays of this dual species and so on. So it turns out with this technology, maybe I won't go into too many of the details. Maybe I'll kind of stop at this point because I don't want to go over time. For example, here's an implementation of the GHZ state using this, let's say this dual species Rydberg atom implementation in the sense Arcturus implementation. So, so what you do is you let the atoms interact. The native interaction between the atoms actually implements the CZ gate, the gate that you need to go from the product state into the cluster state. Okay, so as long as you run that gate, run that interaction with the right amount of time, which we call SPT. So this is really the fact that this cluster state is a topological phase is why we're calling this TSPT. If you do it, just right, so as you approach the correct amount of time, you see this correlation length becomes extremely large. Correlation length tells you how good a GHZ state you have. If you think about it as the spin-spin correlation function, it's really the how long this is in terms of the lattice spacing. You see that it exceeds, it can go up to 1 million. And of course, I'm sure other things will come in before that happens. If you actually had 1 million Rydberg atoms, they're a micron space. We're talking about something that's a meter size, right? So of course, there are other issues that are going to come in before that. But it tells you that even keeping all these further neighbor interactions, they don't mess up the state that you get. You can even be off in the time. You can be somewhat off in the time that you run the protocol. You make an error that restricts, that kind of limits your correlation length, but not by a whole lot, right? And at some point, the size of the system is going to intervene, so you don't have to be that close. So this on the right is actually looking at fidelities for actually doing this protocol. So imagine you do some you do some pulse in order to get the product state that you want, and then you do these gates. Of course, the interaction is on when you're doing the pulse, so it's going to affect the fidelity. Even then, you get extremely good fidelities, and we can extend this to get all kinds of other states like toric codes, Facton, topological orders, and in fact, we are finding that many of these states that people thought are hard to find, hard to make, even things with non-abelian topological order, with sufficient ingenuity with these kind of gates and measurement, you can get these states. Okay, so anyway, I think this is an exciting kind of direction to go in, and maybe I should end with my joke. I shouldn't forget to give most important slide in my. Okay, so really, this is fast, preparation for long range, entangled states.
Slide, you might have stopped sharing the most important joke slide.
That would have been terrible. Yes. So I was trying to look up, something relevant for this, and there are these two movies that popped up, right? This series, favorite of Norm's, I'm sure, but there was this one, Slow and Measured, right? So this is really trying to combine the best of both worlds. And this one is on the archive, and the other one should come out soon. All right, let me stop over here.
Awesome. Thanks, Ashvin, for that wonderful and exciting talk. Quite a number of questions. Francisco Machado asks, one point that you emphasized throughout the talk is that the spin liquid is usually nearby and competes with other forms of order, so the region of spin liquid behavior is typically small. Does the same also occur for the fractional quantum Hall effect and we're just lucky to miss it? Or is there a more robust fundamental reason why we don't have this in the quantum Hall setting?
Yeah, that's a really great question. I think it's got to do with the fact that the magnetic field, gives you a situation where really the ordered states are not very good at lowering the energy. That's ultimately the reason that, it's not a one size fits all, that order always wins. But we have some understanding of this in the quantum Hall setting, that when you form the quantum Hall state, that's extremely good for repulsively interacting particles to stay apart from one another. And it also helps that they're electrons. But when you're talking about bosons in a magnet, spins or bosons, they like to order. And the analog of the magnetic field is frustration, where you try to have competing ground states and and try to make order not that favorable. But we're not very good at it, at least for qubits, for spin a half. There are indications that you look at higher spins, like SUN spins. You have n flavors, and all of them can quantum fluctuate. Then the disordered states or the spin liquid states have a better chance.
Got it. There's a question from Bing Tian Ye who says, you mentioned that there are many types of spin liquids. In the context of the Rydberg blockade, do you expect other types of spin liquid order to emerge in other forms of the model, or is Ising gauge theory the only thing that's possible here?
Yeah, so Ising gauge theory is by far the most natural, especially when you have qubits. There are some proposals for things like Z3 gauge theories or more exotic non-abelian gauge theories, but all of the simple ones that have qubits as their inputs are the Ising gauge theory.
Got it. We have a question from Emmy Simon here. Emmy asks, it seems like there's a wide variety of powerful conventional diagnostic tools in the context of quantum materials, including charge transport, thermal transport, scattering, etc. Do you see there being unique things one can learn from measurements that are kind of uniquely accessible only in AMO systems?
Yeah, so for example, the string order parameters, right, that we talked about, it requires you to take a photograph of the system many times and then calculate that order parameter that is actually a multi-body order parameter. It's not just that, it's non-local involving two spins very far apart. It involves a whole bunch of spins, a whole string of them. So these kind of string order parameters, there's no way to do that in a solid state system. So that's one thing that is really unique, I think, to these, where you have site-resolved ability to measure things. The other kind of related thing is, we talked about preparing these states, fast preparation of these states. You've got to measure half the atoms. I don't know any way to do that in a solid state system. If you can do that, get rid of those atoms and look at the rest, then you have this highly non-trivial state. I don't know any way to do that in a solid state system.
Got it. Sam Letter asks, in the dual species Rydberg systems you were mentioning, can the interactions between the same and distinct flavors of Rydberg atoms be tuned independently?
Yeah, that's a very good question. And in fact, I think there are people here who can answer it much better than I can. There are these things called Foster resonances that, for example, what we want in the setup is we want the inter-species, AB species interaction to be bigger than the AA and the BB. That's something that you can achieve in these dual species systems.
Okay, maybe one last question. In the context of the measurement-based preparation of Tor code from the cluster state, for example, it seems like depending on the measurement result, one may need to make a manipulation on the system to get either to a low energy state or to a particular eigenstate. If one adds in strong interactions and moves away from an exactly solvable point, does one know exactly what those rotations need to be after measurement?
Yeah, that's a good question. So one of the things I didn't really talk much about is, in fact, this property of you go and measure half the atoms and you get this long-range entangled state. It's not just a feature of the cluster state that you begin with. Anything that's in the same SPT phase will end up giving you that property. But what you get at the end of the day is not the fixed point wave function. So to give you an example, which we know that the cluster state is like a 1D SPT. Another example of the 1D SPT is the Haldane chain, the spin 1 chain in one dimension, and you can just take nearest neighbor antiferromagnetic interaction, spin 1. You get a topological phase, the same universality class as this cluster state. Now, if you go and measure half the sites there, it turns out you also get a GHZ state, but you're not in the fixed point limit. It's kind of like you're in an ordered state of the Ising model, but not at the perfect cat state kind of limit.
Got it. Sorry, go ahead.
Yeah, I think that was the.
One last question. Turns out it was just one that was just added. Tommy Schuster asks, are there any Rydberg blockade constructions for 3D topological orders? For example, the x-cubed fracton order?
Yeah, okay, so that's, yeah, I mean, the answer is yes. That's the construction. So yeah, actually this one, it's a bit easier to do a slightly different fracton order, which is called this fractal spin liquid. This is due to Benny Yoshida. But this is also a fracton kind of order that, it has restricted mobility particles, line operators, etc. But it ends up on the Sierpinski triangle if you look at it in cross section. And you can achieve this with qubits, very similar kind of protocol, qubits on the sites and the midpoints of the bonds. You do this cluster kind of gate, you do measurements, and you can check, and this fidelity is pretty good as well for getting the state. And you can improve it if you're willing to process stuff later, you can improve it. And you can do the X-cube model as well. I think we've not analyzed it in as much detail, but there is a protocol for that as well. Yeah, so all of these are kind of stabilizer based systems. So in some sense, you can think of these as some very efficient way of measuring the stabilizers, at least when you're in the fixed point limit. But it turns out you can go beyond the stabilizer kind of states as well. That is kind of one of the surprises for us. Not only that's efficient to do this, you can do things that people previously didn't realize was possible by doing this entangle and measure kind of physics.
Got it. Okay, that's wonderful. I think we'll thank Ashvin again for a wonderful talk. Just two quick notes. Let me share screen for one quick second, Ashvin, and just mention that in fact next week there is in 2 weeks there will be there's no VAMO seminar next week, but in 2 weeks on December 17th there will be a VAMO seminar given by Anna Maria Ray on optical lattice clocks, from state-of-the-art timekeepers to an exquisite platform for probing many body physics. And let me also invite graduate students and postdocs to join the Zoom link for the post-seminar discussion. I think Shimon has posted that Zoom link so that folks can join there. So I'll see you all there. Thanks so much, Ashvin.